us summarize what we have learned in the Ramjet engine analysis. We have basically derived expression for various parameters like specific thrust, specific fuel consumptions, and other efficiencies, right? If you look at this thrust specific fuel consumption, we have looked at it and derive this expression. You can note from this expression that thrust specific fuel consumption is dependent on the altitude, right? If you look at A0, and it is the altitude which will tell us whether it is, what temperature and flight Mach number, right? And it will be dependent on how much heat you have added, the tau P, that is the burner or what is called combustors. So similarly, we can find out expression for TSFC, and these are parameters, right? Apart from this, what you call tau B, M0, A0, it is also dependent on tau R, but it is again function of flight Mach number, if you look at. And of course, the kind of fuel you are using, that is heat of what you call combustion, right? And we have looked at propulsive efficiency, and of course here we have using another parameter, that is tau lambda, right? And apart from tau R. So thermal efficiency, it is really doesn't depend on the tau B. When I am saying tau lambda, tau B is inside this propulsive efficiency. So and overall efficiency nothing but multiplication of propulsive efficiency thermal. What we'll do with these equations? You can say, look, we have derived it, but our objective is to carry out a parametric analysis so that we can see which parameter is important, how to optimize, and how to go about under ideal conditions, right? And that's why this is known as on-design analysis. This can be used as a tool for designing anything, right? And keep in mind that we don't have any geometry. We are just talking about, therefore this is sometimes known as rubber engine, like nothing is there, but you are thinking it will be there and then looking at it. So what we will do, we will look at parameters and we will take this, data, that is altitude. Let's say a Ramjet is flying at altitude 20 km, generally it will be till higher altitude. And Mach number, we are varying 0 to 8, of course. 0 I can't say because I have just taken, just to completeness sake, right? And TT4, that is the turbine, that is the exit temperature of the combustors. It is 3 we have taken, 1400, 1800, 2200 Kelvin. And we are basically, let us vary this, use this equation, maybe in a computer program or something to do a lot of calculation. One can do in hand, but generally you can write a small program and then generate data and plot it and see how it is varying and analyze those data also. Plotting is not enough, but you will have to derive some inference from the data. As I always say, that all informations, cannot be converted into knowledge. Of course, rather information doesn't mean knowledge. Knowledge has to be obtained from the information. All information are not data, right? So you need to understand that. So let us see that what we are doing here. We are basically plotting the specific thrust versus the Mach number, right? And for 3 temperatures, like 1400, 1800 and 2200. If you look at this curve, is basically for the 1400 Kelvin temperature, TT4. This is basically TT4, right? If you look at this is TT4. So what you can note from here, the specific thrust with the Mach number for a particular exit temperature, combustor exit temperature, right? It goes on increasing till it attains a particular maximum values at particular Mach number, then again it decreases. Question arises why it is happening, right? And the another interesting thing you can observe, that when the Mach number is 0, the thrust or the specific thrust is 0. Right? If I'll increase this temperature to 1800 Kelvin, you will get the similar features, almost like it is increasing and decreasing, but however its peak value, of course it has increased from the lower temperature to higher temperature, and also the peak specific thrust occurs at a little higher Mach number. Okay. And similarly for the when you go for the 2200 Kelvin, you will have a similar value, only there is a little shift in the maximum specific thrust at a little higher Mach number, right? Only that is the difference, but it is similar, right? But if you look at why it is so, because as the Mach number increases, right, what happens? You get the ram pressure in case of ram engine. So the pressure is higher and you will get the higher thrust, right? Of course you are adding it. But as soon as it will, or when it attains a maximum value, like that is optimum Mach number basically, then what happens? Why it decreases? Because suppose you are flying at let's say 3 Mach number, right, for a lower temperature. So what will happen at the temperature at the exit of your air intake? It will be much higher, and then there is not much heat you can add to the fuel because the restriction on the temperature 1400 Kelvin, right? And as it is so, then like what will happen, some of the things will be really decreasing out, right? Decreases, and it became whatever your energy you are giving, and at the higher Mach number, whether it is coming, so it cannot be converted into thrust because the drag, if you look at the inlet drag, will be much higher. In this case, what we are doing, we are saying this exit thrust, because the what you call high velocity hot gas, right, is coming out of the jet, right, and as a result you are getting a thrust. But here, as I am increasing, for example, like as I am increasing the flight Mach number, then your thrust will be decreasing. Like for example, if you look at M9 V9 minus M0 V0. So as I am increasing this Mach number, if I am increasing Mach number, what happened? These became higher as compared to this, because this is limited by how much heat you can add and how much kind of things. So therefore, as a particular heat input, this will be goes on increasing, so that will negative weight. Therefore, this is decreases. Right? That makes sense to you? Any doubt? Because this part is decreases because your inlet drag is higher with the higher Mach for the same engine. Keep in mind, same engine. So there is another interesting thing you can look at it. That is what you call the specific thrust. It decreases, right? Like at a lower Mach number, it is quite high, and as it Mach number increases, flight Mach number I mean, then it reaches a small value. Then after that, it goes on increasing, but in a very, very low. So if you look at, but in this region, like where the Mach number is very low, although you are getting a specific thrust in this Mach number, but the TSFC is very, very high. But when what happens at the zero, it will be infinite, very, very high. That means it is having no meaning, like that way. Therefore, the problem of zero static thrust as the Mach number 0 is really a critical problem for the Ramjet. So you can also note that TSFC goes on decreasing as basically you are decreasing the temperature. Rather, in other words, when I am increasing the exit temperature from the combustors, the TSFC goes on, which is obvious because as you want higher temperature, you need to consume more fuel. Right? So if you look at the propulsive efficiencies, these are basically what you call is increases with the flight Mach number for the same temperature. However, the thermal efficiency doesn't depend on the Mach number, on the increase in temperature, but it does depend on the Mach number because it goes on increasing with the flight Mach number. And overall efficiency multiplication of 2, you can see these are the overall efficiency which is increases with the flight Mach number, right? So I mean, this is the thing what we have learned in this, and we can also carry out several parametric variations, try to understand what is happening with this equation. So let us start this lecture with a thought process. As eyes without light, heart without love, so human life without freedom is meaningless. So let us look at what we learned in the last lecture. We have basically looked at Ramjet engine and carry out the analysis, and we have also looked at a parametric studies, right, and how this thrust or the specific thrust will be varying with Mach number for a range of temperature. Temperature means combustion exit temperature, combustor exit temperature. And we have looked at propulsive efficiency, overall efficiency and thermal efficiency. Now what we will do, we will be looking at basically an example and use those expression and do that. And I will take the same example and use another method. You can say this is the method 1. I am doing that. No, okay, method 1. So what is that? An ideal Ramjet engine flying with a flight Mach number 2.5, altitude of 20 km, maximum allowable temperature is 2200 Kelvin, and we'll have to determine specific thrust, specific fuel consumption, and all other efficiencies, right? And these are the given, like altitude is given and temperature T4, all those things I have already talked about, and CP we are assuming 1.005 kilojoule per kg Kelvin. So this is the process what we have looked at, TS diagram, you know, like 0 to 1 is your basically compression or ram compression, and this is the heat addition combustion from T to station 2 to the 4, and this is your expansion is the nozzle, right? So what we will do, we will basically know these values, we will look at it kind of things and then do the needful, right? Method 1, as I told you, we have already derived those expressions for the specific thrust. So what we will do, we know these values. This is 2.5, right? Do you know that? And we will find out A naught. Of course, we know altitude, we know the temperature, right? And knowing that, we can find out A naught is equal to root over gamma RT, right? So that is A naught is equal to root over gamma RT naught, and we get this 290. So we know that, right? And if you look at the specific thrust is, I mean, like, you know, then we need to find out tau B, right? Tau B is, what is that? By definition, it is TT4 by TT2. We know TT4, that is 2200 Kelvin, which is given, and we need to find out TT2. So how we'll find out TT2? TT2 is equal to TT naught, right? We know T naught into 1 plus gamma minus 1 divided by 2 m naught square. We'll substitute these values, right? This is given from the altitude to 16.6 Kelvin. When you substitute values, we'll get 487.37 Kelvin, right? And then you substitute, we get these values. And once we get these values, right, we know basically whatever the parameter in specific thrust, that is A naught is known, M naught is known, tau B is known, so you can substitute those values and get the specific thrust. So if you look at, I am just substituting these values, and then I am getting 8.71 Newton per second per kg, right? Because it is per unit mass of air flow rate. Right? Specific thrust is being thrust divided by the mass flow rate of air, which is entering into the inlet of the engine. So the expression for TSFC can be used to evaluate its values, right? We know this by definition. CP, T naught, and tau B is already evaluated delta S is known, A naught is known, M naught is known. You just substitute these values and you get. So do you know this tau R? Tau R is a very simple thing. What you will have to do, tau R is equal to 1 plus gamma minus 1 divided by 2 M naught square. So I know these values, I know gamma, so I can find out very easily. And tau R is basically what you call Tt naught by T naught or Tt2 by T naught, whatever. Rather, the basic definition will be T naught. So if I substitute these values, I will get 48.2 milligram per Newton second. I put in milligram so that it will be easier to remember, keep it. Otherwise, you can put in SI unit kg per Newton second, right? And propulsive efficiency can be determined very easily. And 60, if you substitute this tau V in this place, you will get 64.0. Keep in mind that I need to multiply by 100, right? So in percentage, we always feel comfortable. Therefore, we put that, right? So similarly, thermal efficiency, we know this tau R 2.25, and you can get 55%, right? And when you multiply these things, right, you will get the thermal overall efficiency 35.57%, even under ideal condition, which is quite a low value, if you compare to your other engines, right? Now, what we will do when you are doing this thing, you don't have a feel about, let's say, what is the exit Mach number, right? Or what is the exit velocity, and what is really happening, right? So, and also there is another way, of that you need to remember those, formulas, particularly in examination. So, what we will be doing, we will be looking at direct, this one, and look at each point, like station points, and see what we can do. And sometimes we may use this, methodology to some extent to make it simpler. But this will give a physical feel when you are looking at it. But those things, whatever we have derived, those expressions are meant for computer programming. So it is more mechanical in nature. So I would ask to use the method 2, particularly while you are solving and try to understand the problem. But whenever you want to mechanize it, or you want to do several repetitive calculations, right, then you can adopt the method 1, and which is essentially designed for what you call parametric studies. And in nowadays computer is available, you can use that very easily without really thinking much, right? So what we will do, we will basically looking at specific thrust is equal to V9 by minus V0, right? And of course we are assuming P9. What is this V9? V9 is root over gamma RT, 2 divided by gamma minus 1 PT9 by 9 power to the gamma minus 1 gamma divided by gamma minus 1, right? So that means I need to determine this T9, I need to determine this P9. Do I know really P9? P9 I know, it is nothing but your P9, okay? But do you know the P9? You know the altitude, so you know the P9. So similarly, you will have to find out PT9, right? And V0 we need to find out. That is a very simple one, which is same as that of the previous method, that is A0, M0, and you just substitute these values, you will get 737.5 meter per second. At least you are having a feel what is V0. But in that other method, you do not know really. You substitute the values of M0, and you do not know what will be the velocity with which the Ramjet is flying, right? Or the so that gives a feel. And as I told you earlier, what we will have to do, we will have to basically find out from here and go to this point, find out various properties, pressure, temperature, whatever it is required. Similarly, I will have to go this point to T4, right, 4, and then find out what will be the temperature T4 if it is not given. If it is generally it is given, or sometimes you need to find out, that you do not know really, and you have to cross check whether it is that. And then of course this you need to know, or you have to find out. In this example or ideal situation, P9 is equal to P0, so you know. But when you go for a real cycle, you won't be knowing this. You need to find out. P9 won't be known some cases. So let us evaluate this Pt9 by P9. You can use this method, or you can go by some other method also, step by step. So these are the same thing I have done. So if you look at this phi d will be what? Phi d will be 1, right? Phi n will be 1. And what about pi b? Can I say it is as a 1? Right? And pi b is also will be 1, because there is no pressure loss in the total pressure loss in the burner, so this will be also 1. So that turns out to be pi r. And pi r you can find out very easily, so that you know this pressure ratio, and Pt9 you can find out. I mean, you need not to, you can really substitute these values and find out M9 is this much, 2.5. And interestingly, this M9 happens to be same as that of the, what do you call it, flight mat, and that will be valid only for an ideal case. So now in order to evaluate speed of sound, A9, I need to find out T9. T9 you can find out T9 by this what do you call it, T9 kind of things, and you will get that it happens to be 977.8 Kelvin. So using having two equations, we can evaluate V9. I know this V9 and I know the M0, I can find out. So this V9 happens to be 1567 meter per second, and which is not same as the flight velocity, which is 700 odd numbers, right? So when you substitute these values, you will get 829.5 Newton second per kg, and you will see that it is almost same as that of the earlier method. So in order to estimate TSFC, we can evaluate all those things: CP, delta SC, TT4 minus TT2. Right? This is, we are not using tau b, tau r, but you can put that it happens to be 0.04. And keep in mind that this is what you call a ratio, right? So using this we can find out TSFC is equal to F by TS, that will be 4.82 into 10 power minus 5 kg per Newton second, and which is same as that. So propulsive efficiency can be evaluated as V9 by V0, right? And we know V9, we know the V0, so you can get the propulsive efficiency very directly, right? And thermal efficiency is same as that when you substitute V9. And but here you can see that what is the difference, in that velocity, and how much change in the kinetic energy is occurring. You can have a feel for it, where you cannot get there. It is just a number and what is coming. So the overall efficiency will be 35.6. So what I am suggesting that if you want to have a feel, you will go for this method too. And I would urge you people to use in your exam and other places the method 2 unless otherwise stated. Particularly in some assignment I will be giving in some questions where you need to carry out parametric study. Therefore, method 1 has to be adopted for those problems. The rest of the problems, the method 2 is to be adopted. Is that clear to everybody? Okay, so method 2 gives a physical feels. Therefore, it is very essential you should do that to have a feel for what is happening, what you are doing exactly. So now we will get into the turbojet engine. We know that in the ramjet engine there is always problem to get the overcome the problem of zero specific thrust or the specific So as a result, we cannot really make it airborne from the what you call plane itself. right? So you need to have auxiliary units. In order to overcome that, one can think of using a compression. And when you talk about the compression, because it has to give some ram pressure to make it fly, to produce thrust. So for that reason, we need to have add also turbine. So a turbo jet engine, if you look at, it is nothing but similar to the ramjet engine with a turbo machinery. If you look at, there is a compression, and to run the compressor we need the turbine. Keep in mind that the work obtained by the turbine is just meant to run the compression. That is the turbojet engine, and all the thrust is being produced by expanding the gas in a nozzle. That means, in case of turbojet engine, the thrust is produced by expansion of gas in a nozzle. Rather, nozzle is the component which gives you the thrust, not the turbine or the compressor, right? So this is a very important concept you should keep in mind. Unlike the other, particularly turboprop engine, So we'll be using these station numbers like 0 to 2 is your air intake, and 2 to 3 is your compression, 3 to 4 is your combustion chamber or combustor, and 4 to 5 is your turbine, that is expansion, and 5 to 9 is your what you call, of course, 5 to 6 and 7. You can say there will be 7. This is known as the jet pipe, but however 7 to 9 is your nozzle, right? So I have already discussed about this thing. Now we will be looking at how the process is, in a TS diagram. So if you look at this process, is basically what you call compression in air intake, and this is your compression, right? And this is your combustion chamber, constant pressure, heat addition, and this portion is your expansion in a nozzle, expansion in turbine, and this is in your nozzle, right? Expansion, it is similar to that what ramjet, only thing you are having a contribution from compression and a turbine, that's all, but it is similar. And if you look at PV diagram, it will be similar to that, only the division will be there in the compression and expansion process. So now what we will do, we will do the similar methodology to derive the expression for the thrust produced by an ideal turbojet engine will be same that what we had derived at m.9 V9 minus m0 V0. If I take this A0 out, and m0 9 out, I will get V9 by A0 minus m0. m0 is the right mass number. So A0 is the speed of sound, and we have already know this thing, and the specific thrust can be defined as I told earlier. The thrust divided by mass flow rate of air is nothing A0 V9 by A0 minus m0. This is the same thing what we have done. So, right, and we know that V9 by A0 square is nothing but A9 square M9 square, and A0 9 we know that it is gamma 9 R9 T9, and A0 square, that as gamma naught R0 T0. So this is cancel it out, gamma is same as that, so you land in getting T9 by T0 into M9 square. So what we'll be doing, we'll be doing the similar stuff of relating the various pressure and temperature parameters in each component. It's just extension of what we had done for the ramjet engine. So PT9 by P, 9 we know that it can be expressed for isentropic flow in terms of Mach number, and exit Mach number, if I just rewrite back, that it will be M9 square is equal to 2 by gamma minus 1 PT9 by P9 power to the gamma minus 1 divided by gamma minus 1. Right. So we will be looking at this PT9 by P9 and look at various pressure ratios. So if you look at in the similar way, and I have just written down here, and if you look at this is a fully expanded, so this will be 1, and PT by P0, what it would be? This will be your pi r, and PT by PT2 by PT0, this is nothing but your pi d, and this is PT3 by PT2 is pi c, and PT4 by PT3 is nothing but pi b, and PT5 by PT4 is your pi turbine, right? And this is your nozzle, you can say, right? And we know that this what you call, and we can express in this similar way in terms of pressure ratios, right? And under ideal condition, what we can say? We can say that pi b is equal to 1, right? Yes or no? Right? And what happens to your turbine? Pi t, can I say 1? Pi c, I can say 1?
No.
No, no, right? And pi d, can I say 1? Yes or no? Total pressure ratio, what happens in the pi d?
Across compressor, no.
No, compressor, no. Turbine is no. That, as you were saying, right? Because we are, getting something, doing the work on it and extracting the work in the turbine, right? So what about pi d? What we did in the ramjet engine? Total pressure, what is happening?
1.
Huh?
Total pressure, ram pressure.
Ram pressure will be what? Total pressure will be remaining same or it will be different? This is isentropic process, right?
1 होना चाहिए था.
1 होना चाहिए, right? Yes or no? Okay. So, and what about nozzle?
1
Is also 1, right? Because we are just converting, kinetic energy into the where? Into the static pressure, or the dynamic head to the static head in case of your air intake, and this is other way around. The nozzle just opposite. The static, static pressure we are converting into the dynamic head, right? But the total pressure is remaining constant. So therefore, you will have to be, understand this concept. So pi n, pi b, and pi d is equal to 1. So this equation becomes, like Pt by P9, pi t, pi c, pi r. In case of ramjet engine, pi t is equal to 1 pi c, because there is no compressor, no turbine. So you can directly get this expression. That means if I know this equation, expressions, I will get ramjet, turbojet, just making some parameter 1. That is the beauty of this analysis, right? I need not to do anything. Okay. If I say pi t, pi c is equal to 1, that means it is a ramjet, right? That is the beauty of this relationship, where computer you can do very easily. I can put a condition and do that. Ramjet, scramjet, same equations, So that you must appreciate of this relationship, and using equation 3 exit Mach number I can get, because I have already derived, that is nothing but same as that, and except this pi t and pi c being come into as compared to the ramjet engine, right? So if you look at this, similar to that, what we have done for the ramjet, only 2 terms have come for the turbojet, pi t and pi c. So whereas the pi r is, we can relate to the tau r gamma power to the gamma minus 1, and similarly for pi c and pi t, these are isentropic relationships. Pi means it is the pressure ratio, tau means it is the temperature ratio. So we know the pressure ratio can be related to the temperature ratio with the help of this gamma, or the index. So M9 square, you can write down here itself if I put these values over in this place, and also for pi r I can get instead of pi I can get in terms of tau, that is tau t, tau c, tau r, right? So we will do the similar way of getting this T9 by T0. We can write down T9 by T0 divided by T9 by T9. And we will go on doing that, all those things. If you look at it, you will get this tau n, tau t, tau b, tau c, tau d, and tau r. If you look at tau d is what? Is it 1? Because it is an adiabatic process in the air intake. There is no heat, so therefore that will be 1. Similarly, in the nozzle, is it you are adding some heat? You are not doing anything, so therefore it will be 1. So what about tau c and tau t? Can I make it 1? And tau b certainly no, because I am adding some amount of heat, right? Can I make it? I cannot make the tau t and tau c as 1. That means the total temperature across the compressor and across the turbine are changing. So it cannot be 1, because in one case compressor you are giving amount of work, and in the turbine you are extracting the work from the fluid. So there will be change in total temperature. Otherwise where you will get anything. So therefore you cannot really make it 1. So Tt9 by T0, it will be tau t, tau b, tau c, tau r. And again you can say this here, you can appreciate this point, that tau c and tau t will be 1 in case of Ramjet. Right? The same thing I am repeating so that it will enter into your mind. So the expression T9 by T0 can be really, if you look at it, is interesting. If I put this Tt9 by T0, all those things, this is and also Tt9 by T9, you will see that it can be cancel it out, this can be cancel it out, and the tau c can be cancel it out. It happens to be tau b. And what we had seen in case of your Ramjet engine, yes or no? We are doing the same thing, but making it a little complex, but this is cancel it out, which is obvious, because the in the turbojet engine, the work harnessed by the turbine is being utilized by the compression. Therefore, it must be T9 by T0 will be tau b. It will be how much it added into the combustors. Right? That is the thing what is saying, and it is true also Ramjet. So the Ts, you can just substitute these values, V9 by V0, right? And you will get an expression which looks to be little frightening, but however it is quite simple to. I am not expecting that you should remember this expression, but however you must know how to go about, how to derive it. That is expert, right? So, and which will be quite simple to derive these expressions. And very important, we need to now relate this turbine work into the compressor work, because we will have to get a relationship between the compressor and turbine. So we will assume the one-dimensional steady state energy equation, this thing, and we will apply this to energy equation, control volume, and the turbine work will be m.5 is equal to st5 minus st5, right? Because in the turbine, and you keep in mind that here we are assuming, like the mass continuity is maintained, because one dimensional flow we are talking about. So m.5 is equal to m.4. You are not adding anything except, so same fluid is going. So therefore, which is nothing but that m.0. Keep in mind that here I am saying it is very, very less than m.5 or is very, very less than m.0. So therefore I am saying this is m.0 is equal to m.5. Basically m.5 is equal to m.0 plus m.0f, right? But I am assuming this, so therefore m naught f Cp Tt4 minus Tt5. Similarly, I can have for compression, which is same as that m naught Cp T3 minus Tt2, right? And when we equate this, the work done by the turbine is same as that of the work, taken by the compressor, then we'll get an expression, tau T is equal to 1 minus tau R by tau lambda in the bracket tau C minus 1. Keep in mind that we can express in terms of tau lambda, because that is the thing, how much heat, being added, or the total enthalpy at the exit of the combustor divided by the amount of enthalpy is entering into the engine, right? So if you look at it, is the, you can rewrite it, because this will cancel it out, Tt4 by Tt3 into Tt by Tt2 into T2 by Tt0 and Tt0 by T. So you can write down in terms of all this tau B, tau C, this is the compressor, and tau D is for the air intake, and tau R, and you know that tau D is equal to 1, and right, because of it is a adiabatic process, we are saying no heat is going out, but in real situation it cannot be, but ideal under ideal situation is okay. So the fuel air ratio can be expressed in terms of known variables, as we will have to consider these combustors, which we had done a similar thing in case of a ramjet engine. It will be same. So we can write down m dot f divided by m dot a is nothing but Cp T naught delta Sc, which you will see that tau B, tau R, tau C minus tau R, tau C. You see, this some step I have omitted here, but you can do very easily, and in case you will find some problem, you let me know, right? And TSFC you can get very easily, that is F divided by specific thrust, right? And you will put these values, now we are having several terminologies are coming, like several ratio, temperature ratio or pressure ratio. Keep in mind that we can, change this tau C in terms of pressure ratio of compressor. Similarly, tau T, we can, some places wherever it is required, we can change into the pressure ratio across the turbine, right? And using the isentropic relations. So the relationship for propulsive efficiency, we can write down 2 TV, basically the thrust power divided by kinetic energy change in the engine, that is m dot V9 square minus V0 square divided by 2. If I just write in place of thrust this expression, m dot A into V9 minus V0, you will see that I can cancel it out, and this will cancel it out, and I will get V9 plus V0, right? If I divide it by A0 square here, and similarly A0 square here, I will get 2 right Mach number divided by V9 by V0 plus M0. So this is the easier way of saying that, because I know expression V9 by A0, I can do very easily, right? And also you can see that how this Mach number is really affecting your propulsive efficiency and thermal efficiency. You can get, do all those things algebra, and you will get 1 minus divided by tau or tau C. Keep in mind that here tau C has come into picture in case of turbojet, right? Earlier it was only 1 minus 1 over tau R in case of ramjet. Tau C is equal to 1, right, in case of ramjet. So overall efficiency will be nothing but propulsive efficiency multiplied by thermal efficiency will give me overall. That means by this we have derived all the expressions. We are armed with all the expressions to carry out parametric studies, right? And just to summarize those whatever we have derived, like I will that is the specific thrust we have done, and these are the expression which is terms of various tau t, tau c, tau r, and we are using also tau lambda, and in place of tau lambda maybe this term tau lambda divided by tau c, tau r is nothing but tau v. Some places you can use tau v as well, right? So what is helping this specific thrust expression is basically separating each parameters, and it is arming with us or helping with us such that we can do a parametric studies. That you must appreciate. Otherwise, I need not to go for this, unless I am not interested in parametric studies, and which is essential when I am trying to understand, how it is the performance is affected by the various parameters. Right, the TSFC, and we know that F is, it can be expressed in terms of tau B, tau R C minus tau R, tau C, and multiplied by CPT naught beta S. And these are expression for propulsive efficiency, thermal efficiency, which we have discussed just now. And what we will do now, we will take three cases. One is the Mach number of 0, right? That is the sea level conditions, and another will take the long range, vehicle or the aircraft what we use, passenger aircraft 0.85, which can operate at 12 kilometers altitude, and then the fighter aircraft, which is corresponding to 1.5, 15 kilometer altitude. And we are keeping this, the turbine, like inlet temperature or the combustor exit temperature 1600 Kelvin, right? Okay. So, and what we will do now, what are the variables we will be using? We will be basically using the, we can vary these pressure ratios across the compression. You can say that why not vary the pressure ratio across the turbine? You can do as well, because both are, can be related easily with the work, because the work, whatever you are getting from the turbine is being utilized by the compression. So generally compression is a very important one. So therefore we use the compression as a parameter that will be varying from 1 to 40, and see that how we can choose a compressor, how we can choose a pressure ratio, because the compressor size and cost will be dependent on the pressure ratio you want to have for an engine, right? So that is a very important one. So what we are looking at is the specific thrust, right, being plotted on the y-axis, and the pressure ratio plotted on the x-axis for a turbojet engine, which is having turbine inlet temperature of 1600 Kelvin, right? And we are also varying this Mach number. As I told you, three cases we have taken, representative case. One is sea level condition, or you can say static conditions, right? Other is 0.85 Mach number, flight Mach number, and other is 1.5. What you can note here, that when this flight Mach number is 0, this is a solid line, the specific thrust increases with the increase in pressure ratio across the compressor, and then it reaches a peak values here, and then after that it decreases slowly, right? So what it indicates, that means there is the optimum value for the what you call pressure ratio across a compressor, for which you will get the maximum specific thrust. And however, if you look at the TSFC, which I have shown here, that is, it is a very high values at the pressure ratio of 1, because we cannot have 0 pressure ratio across compressor. So 1 is the, that means no compressor as such, right? At that value, it is going towards infinity, very, very large. It's having no meaning. I mean, you can't have any meaning in turbojet engine having a pressure ratio of 1, right? Okay. But however, it decreases, and it decreases continuously as you increase in pressure ratio, you will see that this is having not a minimum values, right? Unlike in a Ramjet engine, there is a minimum values, right? And of course you will have to choose that, but there is another interesting thing you can observe. When I'll go for the flight Mach number of 0.8, you will see that this is having, it also having similar feature. It goes on increasing, and then of course it is having a certain values of 20 kind of thing, where you get the maximum specific thrust. But if you go for a flight Mach number of 1.5, you will have similar features, right? Similar nature of the curve, but only thing it is decreasing, after reaching a value of certain maximum value at a pressure ratio of 9, 5C is equal to 9 you are having, right? And then it decreases little at a higher rate as compared to the both the sea level condition and or the static condition and the flight Mach number 0.8. What it indicates? It indicates that when the flight or the engine is moving at a higher speed, it can use that pressure, and you need not to go for a high pressure ratio compression, because the ram pressure can be utilized, right, to for increasing its pressure, right? So therefore, it is, if you look at the fighter aircraft, will be having a smaller compression because you need a very low pressure ratio. Whereas you go for a long range passenger aircraft, you need to have a go for 20 kind of things, right? But at the same time, you will have to look at what specific thrust you need, because at a static condition, because static thrust is also important. So you will have to play around and see that what really you need and what is the level flight. So these are the things you can get by just doing, specific parametric analysis, right? That is the beauty of this method. That you can learn a lot by just playing around and see what is happening, why it is happening, and what are the reasons, whether you can have any scope to improve it further or not. So let us look at propulsive efficiency and the thermal efficiency. If you look at these are the curves, which is basically the propulsive efficiency, these two curves, and it is a static condition. There will be no meaning of having propulsive efficiency when Mach number, flight number is equal to 0, right? So whereas the this one is basically Mach number of 0.85, it is having higher propulsive efficiency as compared to 1.5, right? But it is having similar features in the when its pressure ratio increases, right? It is very higher over here and decreases maybe at certain pressure it is minimum, which is not very obvious in this diagram, but when you look at number you will get that. And thermal efficiency, it is goes on increasing, like from the lower pressure ratio to higher pressure ratio, and you will get a lower thermal efficiency case of 0 flight Mach number, and when you increases this 0.85, you will get a thermal higher efficiency, and when it is the 1.5 kind of thing, this one, then it decreases because of your energy utilization point of view. So what we will do now, I will just look at what happens, the effect of temperature ratios, and which is having similar views. You can see that this is having highest temperature, like 1800 Kelvin. So if you look at, you will have a higher pressure ratio you need to get a higher specific thrust, and as the temperature decreases, you will get a lower specific thrust, like a maximum specific thrust at a lower pressure ratios, right? Why it is so? Because you need to have a higher the temperature to be achieved, right? So therefore you need to give more amount of pressure, and you can get a higher kind of values, and after that it decreases. And so and whereas of course the higher temperature when you want to get, and you want to get also higher specific thrust, so naturally you will pay a penalty for having a higher TSFC and having similar view, vertical trend. Like as you goes on decreasing the turbine inlet temperature, you will go on decreasing the TSFC. So you will have to make this thing where you want to go. And with this, I will stop over. In the next class, we will take an example to see how we can, solve this problem. Okay.